Good evening, my name is Gareth Morgan, and this evening I'll be presenting on physically based shading. This talk was originally presented at Papers We Love San Francisco. This is an expanded version of a mini talk I did for Papers We Love. If you've never heard of Papers We Love, it's a really cool organisation. They meet about once a month, and a member chooses a computer science paper that they really love and talk about it for either 15 or 45 minutes. The San Francisco chapter is on Meetup at this URL here. If you're interested, you can check it out. The material in this presentation comes from Brent Burley's 2012 Siggraph paper, Physically Based Shading at Disney. I really like this paper. I think it's a good overview of physically based shading, as well as a good description of how Disney Animation Studios implemented physically based shading in their renderer. I've not covered all material in the paper in this talk, so I'd recommend you download the paper at that URL there. So what is physically based shading? It's become a bit of a buzzword, particularly in real-time graphics in recent years. What does it actually mean? I think these two pictures kind of demonstrate what physically based shading is. On the left, we see a shot from the original Pixar Toy Story movie. And if you look at the surfaces in this image, they look kind of unrealistic. They look flat and plasticky, which of course is fine because the characters in this movie were meant to be made of plastic. But if you compare those surfaces to the ones on the right, where you see an image from the recent Disney movie Zootopia, you can really see the difference. If you look at the fur and the fabric in this image, it looks like real fur and real fabric. The way light interacts with that fur and with that fabric is a pretty good approximation of how real light really interacts with real fur and real fabric. That really is what physically based shading is about. It's how do you achieve that approximation of the real behavior of light and how it interacts with surfaces. So I'd like to step back a bit first and explain what does shading mean in the context of physically based shading. So to answer that question, you kind of have to take a look at what's actually involved in computer graphics in rendering an image using a computer. Basically, computer graphics all boils down to one question. For a given point in the scene, how much light will reach our eye from that point? So in this example, we have our eye here at point X on the left, and we want to say how much light will reach our eye from our point X prime on the right. To answer that question, you actually need to know how much point arrives at point X prime from all these other points we're calling X prime prime in the world. So it's a recursive problem. But in terms of physically based shading, the important point is that not all the light that arrives at our point X prime from our point X prime prime will get reflected and ultimately arrive at our eye at point X. In fact, only a really small percentage of that light will ultimately arrive at our eye at point X. The purpose of a surface shader is to come up with an algorithm that decides what that percentage is. How much of the light for a given point X prime prime arriving at a point X prime will ultimately arrive at our eye at point X. That's the purpose of a surface shader. To do this, mathematically speaking, what we're actually doing in our surface shader is implementing what is called a BRDF. A BRDF is a really important concept in computer graphics, so I'm going to dig a bit into it in detail. A BRDF stands for bidirectional reflection distribution function. And it's a function that defines how much light is going to arrive at our eye in a particular view direction with a particular light direction. That is, here at the top of the slide we have our light. We have some light travelling along the blue light vector labelled L. It's hitting the black surface at the bottom, and it's being reflected along our yellow view vector V to our eye. The BRDF tells us what percentage of that light is going to get reflected in the right direction so that it ultimately arrives at our eye. To define the BRDF, we need a bit more information. Firstly, we need to know the normal of the surface. A normal is a really important concept in computer graphics. If you've ever touched on computer graphics at all, you've probably encountered a normal vector. It is the vector that is exactly perpendicular to the surface at the point we're interested in. As well as this normal, and it's a three-dimensional vector labelled here, the blue line labelled M. As well as that, we also have, it's also useful to define what we call a half vector. That is the vector that is exactly midway between the view vector and the light vector. Here it's labelled H, and it's shown in yellow. So now we have these four vectors, we can define the parameters of our BRDF. The way I'm defining them here is the way Brent defines them in the paper. There are other ways of defining a BRDF, but I'm going to stick with the way Brent defined it. So first, you define it in terms of a set of angles. The first angle is theta L, which is the angle between the light vector and the normal. The second angle is theta V, which is the angle between the view vector and the normal. The third angle is theta H, which is the angle between the normal and the half vector. And the fourth angle is theta D, which is the angle between the half vector and the light vector. Then finally, this is a two-dimensional diagram, but the scene we're describing is a three-dimensional thing. So phi is actually, if you can imagine rotating the light vector out of the slide around the half vector in 3 dimensions, that value, that angle is the phi vector. So we have these 5 vectors that are the input to our BRDF function. So we have a 5-dimensional function. Unfortunately, humans aren't particularly good at kind of visualizing 5-dimensional functions in their head, so this can be a bit tricky to think about. Fortunately, along with the paper, Disney Animation Studios also published this bit of software, the BRDF Explorer. It's really downloadable from the Disney Animation website, and it's a really cool bit of software. This software actually plots a BRDF in 3 dimensions in a way that humans can hopefully kind of understand what's going on. So at the bottom pane, we see an image of a sphere that's been shaded with a particular BRDF. That's actually, this is what this BRDF would look like if it was applied to a sphere. More interestingly is this top pane. This is a 3-dimensional plot of a BRDF. And this is actually where most of the diagrams in the rest of this presentation are just screenshots from the BRDF Explorer. So I'll dig down to exactly what's being shown here. Here's an image taken from the BRDF Explorer. So just like in the diagram I drew earlier, we have the light blue light vector on the left, L. We have the dark blue normal vector, N. And then we also have this pink vector, which is the reflection vector. That is the result of reflecting the incoming light vector around the normal to produce a reflection vector. And then the BRDF itself is drawn as this weird red shape here. So every point on that BRDF plot represents the distance of that point from the origin represents the value of the BRDF for that particular view direction. So here we can see for this red BRDF object that it's 0 throughout most of the unit sphere. So for most view directions, the value is 0. But we do have this big lobe just below the reflection vector. So there's an area just below the reflection vector. And so for view directions in that area, we have some non-zero values. And then we have a second lobe almost parallel to the surface itself. So at really glancing angles, then we have another region where we have some non-zero values. But other than that, pretty much the whole sphere is 0, except for those 2 values. So here you can actually see plotted visually in 3 dimensions what the BRDF looks like. So BRDFs aren't new. They've been in computer graphics for almost as long as computer graphics has existed. But because of computing constraints, for most of the history of computer graphics, we stuck to pretty simple BRDFs that could be represented pretty simply. And these are probably the 2 most common BRDFs that have been used in computer graphics throughout its history. On the left, there is the simplest possible BRDF, which is the Lambert BRDF. It's named for a 16th century Dutch physicist. And it basically says that regardless of the view direction, regardless of the light direction, the BRDF is constant. The light is constant in all directions. So when you plot a Lambert BRDF, it just forms a hemisphere because it's a constant value everywhere on the sphere. And obviously this is very simple to implement because it's just a constant value. And it does an okay job of simulating a very diffuse, rough surface. For example, the surfaces of this wall, the walls of this conference room, would be okay, rendered as using a Lambert shader. It does fall apart in certain circumstances, which we'll discuss later. But yeah, it's still used because it's okay. It's a reasonable approximation of diffuse surfaces. For shinier specular surfaces, another simple BRDF that has been used a great deal is the Blin-Phong BRDF, named for Jim Blin and Guai Fong. It's a fairly good representation of a smooth specular surface. Basically, the BRDF is 0 everywhere on the unit sphere, except for this tiny lobe around the pink reflection vector, where the BRDF is non-zero, but everywhere else it's 0. Again, although a little more complicated than Lambert, it's still pretty simple to implement. So it's used a lot, and it's still used a lot. I'm actually going to take questions at the end, if that's okay. So just go and interrupt. Yeah, so it's simple to implement and does an okay job of simulating the behaviour of light in a very shiny specular surface. At this point, I'm just going to have a slight digression in terms of colour. In the real world, colour is actually really complicated. Colour is the light that's bouncing around the world is made up of different wavelengths, and some of those wavelengths, when they arrive at our eye, they are represented as colour, that we see them as colour. And those wavelengths interact with materials differently, they are absorbed and reflect differently. It's a pretty complicated subject, but almost universally in computer graphics, it's simplified to just three colours. We have a green, a blue, a red, a green, and a blue colour channel. So all the values I'm talking about, a lot of the values I'm talking about in this presentation, they aren't simple scalar, one-dimensional scalar values. They're actually three-dimensional vectors, where you have a red component, a green component, and a blue component. And the BRDFs themselves are actually, there's not a single BRDF, there's three. We have a red BRDF, a green BRDF, and a blue BRDF. But actually, for the most part, it's even simpler than that. What we actually say is that the BRDF is logically the same between the red, green, and blue channels, but the parameters, the constant parameters we use to define how the BRDF behaves, those are three-dimensional color vectors. So as each value, each constant parameter has different values for red, green, and blue. The BRDF behaves differently for red, green, and blue. But the actual logic, for the most part, the logic is the same for the three different channels. The actual logic of the BRDF remains the same. But for now, that's all I'm going to say on the matter. Just remember that most of the values I'm going to talk about in this presentation aren't actually one-dimensional values. They are three-dimensional RGB values. And then finally, another digression. I'm just going to quickly talk about what BRDFs are not. In real-time graphics, physically based shading is often associated with some kind of cube map reflection or reflection probe system. But that's not actually part of the BRDF. The surface shader, the surface, the physically based shading itself doesn't actually care where the color comes from. As far as the BRDF is concerned, it just takes a color and returns what percentage of that color is going to be reflected in a particular direction. Whether that color comes from a traditional point light, whether it comes from, in VFX, it'll often come from a path tracing, a ray being cast in a path tracer, or it could come from a cube map, or it could come from some complicated reflection probe or spherical harmonic system. It doesn't matter in terms of the BRDF. It's not making any assumption as to where the color comes from. It's simply a function that takes in a color and returns what percentage of that color is reflected in a particular direction. So that's just to clarify that. So as computing power computers became more powerful and more research was done, a whole bunch of different types of surface shaders were developed. The problem was for a lot of and they did some of them did a pretty good job of simulating how certain surfaces behave, and that they generally came with a whole bunch of kind of fairly arbitrary parameters that were passed over to artists to tune them. But for the most part, they didn't really represent any. They didn't really represent how light was behaving in the real world. They were just a reasonable approximation of certain surfaces. So the reason this paper exists is there was a push to make shading more physically based, to actually try and understand how light really behaves, and to then simulate that in a surface shader. So to do that, you first needed to look at some real materials. So BRDF is not something that only exists in a computer. It's not a function in a shader. Real world materials have BRDFs. And in fact, the Mitsubishi Electric actually measured them. This is the database that's referred to a lot in this paper called the Merle database. They took some real-world materials, they glued them to a cylinder like the one shown on the right, then they rotated the cylinder and they rotated the light at the same time, and took a whole bunch of pictures, and they actually measured for each material, they measured its actual BRDF. The result of this was a cube of data. So each slice of the cube, the x direction is the theta h, the angle between the normal and the half vector, and the y direction is theta d, which is the angle between the view and the half vector. And then each slice of the of the Merle cube were the different phi values. So as the light rotated around the half vector, that changes the phi value, and so that's a different slice of the Merle cube. And so as a result, when the measurement is complete, if you have this cube of data representing an actual real-world BRDF. Here are some examples of slices taken from the Merle database. So these are actual real-world BRDFs representing real materials. So the team at Disney, they analysed this database and they tried to work out the properties of these materials and how to simulate them using a surface shader. What they came up with what they call a principled BRDF. This is a BRDF that is based on real physics and how light behaves in the real world. But the problem with actually purely physically based materials is they're not really tunable. Like a real material is either wood or it's metal. You can't tune that to be one or the other. It's just what it is. But the principled BRDF, it does come with a whole bunch of material parameters that are tunable by artists, so artists can define what the material looks like, but at the same time it remains physically plausible. It's still based on real physics. And this is the set of parameters they came up with. It's a fairly long list. Not all the implementations of physically based shading have this many parameters. So, for example, Unity game engine, which uses the same BRDF, only has a handful of these material parameters exposed. But the key point about them is they're all in the range 0 to 1. This is for a lot of other BRDFs, you have these arbitrary parameters, and the range could be anything from like 1 to 10,000. So they're quite hard for artists to work with, and they're also quite hard to blend between. If you want to blend between one material and another, it's quite hard to do. So for the plausible range of all these parameters is 0 to 1, which makes life much easier for artists. I'm not going to go through all these parameters. I'd recommend if you have access to a shader based on based on a physically based shading system, that you would mess around with them yourself. But I'll go over some of these parameters. So the base parameter is the main color. Almost every BRDF has this, where it's there is either diffuse, sometimes called the diffuse color, which is the color of the surface. It's just something that artists need, basically, even if it's not necessarily something that exists in the real world. And then we also have this metallic parameter that defines how metallic the surface is. So if it's 0, the surface is entirely non-metallic. If it's 1, the surface is entirely metallic. And then as it varies between 0 and 1, it interpolates between metallic and non-metallic. There is a roughness parameter that defines how smooth the surface is. So if the roughness is 0, you have a perfect mirror, perfect specular reflection, and if it's 1, you have a completely diffuse surface. And as the roughness value varies between 0 and 1, you end up with in the interpolated values, you end up with this kind of nice, smooth, glossy reflection in the middle there, which looks cool. And again, it's how real it looks good, and it also looks like real materials. Real materials aren't either shiny or diffuse; they're usually somewhere in between. There is an anisotropic value that defines the shape of the reflection. So if the anisotropic value is 0, then the phi value in the BRDF is basically ignored. The BRDF doesn't change with the phi as the phi value changes. But if the anisotropic value is 1, then there is a great deal. Then the BRDF changes a lot as the phi value changes. So you get these kind of long highlights, which again is how anisotropic materials in the real world work. And then finally, there is the clear coat value. This is the idea for it came from rendering car paint, where actually we don't have one surface at this point. We have two. We have typically you have 2 layers of paint, and some of the light strikes the bottom layer, some of the light is reflected off the top layer, some of the light is reflected off the bottom layer. So you have two sets of parameters for the underlying layer, and that's called the clear coat layer. It's a pretty important concept if you want, because a lot of surfaces have that property of multiple layers. So that's how they defined how they parameterized their material. I'm now going to dig down into the actual BRDF they use in the Disney physically based shading system. So the series that's underlying the Disney physically based BRDF is the microfacet model. So this is based on the idea that if you look at what looks like a perfectly smooth surface, if you zoom in enough, it's no longer smooth. You have a whole bunch of tiny little surfaces called microfacets that are pointing in apparently random directions. And the way the microfacet model works, it assumes each of those tiny surfaces is a perfect mirror. So the BRDF of a perfect mirror is very simple. It says that the BRDF is 1 if you're looking directly along the reflection vector, and everywhere else it's 0. So then it uses statistical methods to work out how many, to work out how the light is reflected off these millions of tiny facets. An analogy would be, if you're familiar in physics with how thermodynamics works, that you don't try and model the collision of every atom with a particle of smoke, or but you use statistical methods to say, actually we're not trying to model each atom as it collides with an object, but we know statistically as the temperature increases, we can model statistically how gases will interact with an object. And using these statistical methods, you can actually very accurately work out how gases behave. This is a similar concept, but instead of talking about gases, we're talking about how light interacts with the surface. So in the microfacet model, you then take this approximation, and you do some statistical magic, which I don't entirely understand and won't pretend to, and came up with this BRDF, the microfacet BRDF. So it has 2 components, and it's common with a lot of BRDF. You have a diffuse component and a specular component, and the diffuse component is largely view independent, but not entirely, as we'll see on the next slide. And then the specular component is divided into 3 D, F, and G terms, and then normalized by this denominator here. So now we'll dig down and look at these different terms in the microfacet model, and particularly how Disney implemented them. So the diffuse term in the Disney BRDF is this term here. So when they actually looked at the Merle database, they noticed that even objects that you would think of as being perfectly diffuse and having a diffuse shading characteristics, they aren't actually diffuse in the shading sense, that they do change color as the view direction changes. So particularly when the view direction is glancing, as in very close to parallel with the surface, you do actually see some quite dramatic changes in color, which obviously the Lambert shader, which is saying it's constant everywhere, doesn't represent. Which is why they came up with this equation here. And if you look at, so we've actually on the bottom there, you see some slices being rendered, which are similar to the slices in the Merle material database. And you'll see in the center of the slice, where you don't have grading angles, where your angles are close to the normal, your light and view direction are close to the normal, it does look pretty constant. It looks like a traditional Lambert shader. But as you get close to the edges, the top or the bottom or the left or the right of the slice, as you get close to those glancing angles, then you actually get very drastic changes in color. And this simulates how real materials work in the database again here. If you look at these diffuse surfaces, they do have these glancing effects. And so now I'm going to dig into the 3 specular terms. The first specular term is the D term. This is the microfacet distribution function. So you see again, because we're dealing with a statistical model here, what this is basically saying is, you think some of if all the microfacets are pointing directly upwards, you have a perfect mirror, and then you have perfect specular reflection. If, on the other hand, they're all pointing in strictly random directions, then you have a perfect diffuse surface, and you have no specular effects at all. The microfacet distribution function is a way of representing what percentage of the where on that continuum you are between perfectly smooth and perfectly diffuse. It uses this function here, whose name I forget now. I've written down my notes. And we see it looks a lot like the traditional Blindfong model, but unlike the Blindfong model, you can vary it. It's tunable by this alpha component, which changes the shape of the lobe depending on whether the surface is smooth or rough. What we see here, the BRDF plotted in the BRDF Explorer, and an example of a surface rendered just with this one term, just with this D term. The next term is the Fresnel term. The Fresnel term is simply is an approximation of how light reflects off objects. So how this light is reflecting off all our microfacets using and its approximation of the commonly used Fresnel term from optics. And it just relies on the theta d value, and it produces this weird kind of squashed lobe along the normal and the reflection vector that you see on the left here, and then you see the result of that, rendering just that one term in the object on the right. The final term is the geometric attenuation term. So all the microfacets are going to be shadowing each other. So your light, the light from one microfacet is going to be occluded by other microfacets. And the geometric attenuation term, again, using statistical methods, is attempting to simulate that. The equation here is not actually taken from the Burley's paper. It's taken from the paper he referenced, which is the 2007 paper by Black, I believe, and it's what the Disney BRDF uses for its geometric attenuation term. Again, the result is a kind of weird squashed lobe base centered on the normal, and it produces the effect you see on the right there. With all these terms, particularly, with this term in particular, this is assuming we have no anisotropy. There is an alternative version of, both of these, I think, which is in the appendix for the paper, which shows a different version that had a phi contributing factor. Because obviously, if the surface has anisotropic properties, the BRDF varies with the phi value as the light vector rotates around the half vector. And then also, if there's a clear coat component to the parameters, then there are actually two different versions of the specular term. One for the top layer of the surface, and one for the bottom layer of the surface. And so you actually have two completely different specular terms for them with different parameters. And then the geometric attenuation term is simply this kind of squashed lobe centered on the normal. So you put all these together, and you get a result like this. So these four components can basically simulate almost any material really physically accurately. It's really been responsible for a kind of quantum leap in the quality of particularly real-time rendering in recent years. Has been the adoption of almost any engine now will have some kind of physically based shading integrated into it. And it's really been responsible for the kind of quantum leap in the quality of real-time rendering in recent years. Thank you. Are there any questions?